this is compact, and we have a Borel measure on X, say mu X is 1. And we have a measurable transformation from X to itself. It's mu measure preserving. So this is, of course, an ergodic. So this is the general setup for operators of this class. You have seen many times the Lyapunov exponent, LE, associated with this. Limit n tends to infinity of what? 1/n log. Norm of the co-cycle associated with this operator. So A TJX product, J goes from 1 to n. Mu dx normalized limit, Kingman subadditive ergodic theorem, or Fürstenberg-Kästen. This also exists almost everywhere. What is AX? Here, of course, I should indicate the dependence on E. What is AEX? It is the co-cycle matrix associated with this. So we have minus 1, 1. Then we have E minus V of X0. So these are the formulas. And as you heard many times, this is greater equals 0. And the question is, when is this positive? I will, for the most part of my lecture, assume the Lyapunov exponent is positive, but not. Let me not make this assumption now summarily. I can just speak in this generality. What I will look at are eigenvalue parameterizations of finite volume. So what are these? These are the so-called Relich functions. So these are eigenvalue parameterizations of what? Of h nx. I hope you can read this. So this is Pn. I shouldn't introduce too many different notations, but Pn is a projection. Pn psi index n is simply psi n if n is in 0, n minus 1, and 0 else. So this is called the operator with Dirichlet boundary conditions on which interval? On the interval 0, n minus 1. And so here you set the vector psi equal to 0. This is the operator with Dirichlet boundary conditions in finite volume. And then there is another bulk quantity that you get from the ergodic theorem, in addition to the Lyapunov exponent. It's called the IDS, the integrated density of states. This is the integrated I know that many of you are intimately familiar with it. Let me just quickly define it. What you would like to do is you take f, a continuous function on the line, and you want to say that 1 over n, the same n as above, f of ejnx. What am I doing? So summing, this is the trace, of course. What is that? It's another way to write 1 over n trace of f hnx, right? What you would like to say is that this converges to f lambda n d lambda, almost surely in x. So this is, of course, as n tends to infinity. This is mu almost surely. And n here, n is the IDS. So what does it look like? Well, let's compute it for, first of all, why does this exist? Well, because you can actually do the usual trick in trace formulae. Instead of writing the trace in terms of the eigenvalues, which you don't know, you write this trace over delta functions on this interval 0, n minus 1. And as you pass to the limit, you will then recognize that there is a very nice formula for this. Let me write it over here, somewhere where you can see it. Let me get rid of that and say that this converges mu almost surely as n tends to infinity to what? The integral of mu dx of f of hx applied to delta 0, integrate over your base dynamics space, the compact set big X. Where does this come from? Well, it comes from a profound property, easy and fundamental of Hx, which I'm sure you've seen also, that applying the dynamics in the index is the same as conjugating the operator by the shift. And therefore, if you didn't have the boundary condition, you would, of course, be dealing with the infinite volume operators. You have these delta functions. You can shift them around. Then this moves into the Tx with a fixed delta function. But now, of course, you will say that's cheating because you're on a compact interval. You have a Dirichlet boundary condition, correct. But this was a continuous function. The spectrum is compact. Approximate the continuous function by polynomials. Therefore, prove this for monomials. And then you realize that if f is, for example, the function x goes to x squared, x being a real number, then you have the operator hx squared, and then the hopping takes you not just one step to the left or right, but two steps. So the only way that you would see your boundary is a finite distance from these endpoints, and that doesn't matter. That goes away in the limit, and the same argument works in higher dimensions, all right? This has nothing to do with a co-cycle. This works very importantly in higher dimensional lattices. This is all an old story. And that's how you can actually prove that this density of states exists. What does it look like? Can you see? Take the potential equal to 0, then it's a very easy exercise to show that n, which is a measure, so let me write in the sense of probability theory the distribution function. This limit is actually 1/pi times the measure of all x in 0 pi with a property that 2 times cosine x is less or equal than lambda. This is the Lebesgue measure. And lambda, this only makes sense if lambda is between -2 and 2. If you want an explicit formula, this is 1/2 plus 1/pi arc sine, not so important, yeah, lambda over 2. More important is the picture. So you have -2, 2, 0. Then you have the level 1. Then your IDS in the free case. Okay, that is it. And as a reminder, the Lyapunov exponent in the free case, you check all this because you can diagonalize the operator via the Fourier transform. So the Lyapunov exponent, by diagonalizing the co-cycle, is of the form 0 if the energy is in the spectrum, and otherwise it's logarithm of 1/2 absolute E plus root E squared minus 4. Okay, so the Lyapunov exponent, forgive me for drawing this into the same picture, shouldn't do it, is like that, sloppy picture. Important is that the singularities of the IDS are exactly Hölder 1/2, and Lyapunov exponent also Hölder 1/2. So here, these functions, let me just write complete sentences. Ln, this is a curvy n. They are in C1/2 R precisely. Of course, they're much smoother away from the band edges, which is also a very important observation, that these things are actually much smoother away from the thresholds. So maybe, do I have an eraser? There it is. 2 of them. All right. So what is the relation between n, the density of states, the integrated density of states, and the Lyapunov exponent? I'm sure you've seen this in this conference. So there is this famous Tallis formula. Applies in great generality, albeit only makes sense if you're on a one-dimensional lattice, because on a higher dimensional one, you don't have Lyapunov exponents. So that's L of E is integral log minus E prime n dE prime. If you look at this for a moment, you'll see that you can rewrite this. I'm abusing notation slightly. I'm now writing n of E prime, which is this function minus infinity E prime, right? The distribution function of the measure divided by E minus E prime dE prime, which is the Hilbert transform of the density of states at E. Okay. Never mind that you might have qualms about applying the Hilbert transform to something that's constant on a half rate. Doesn't matter because you have perfect cancellation in this Hilbert kernel, right? The constant goes away basically. So these integrals will converge in the principal value sense. And so L and N are conjugate. And since the Hilbert transform preserves, the Hilbert transform is bounded on C alpha if alpha is strictly between 0 and 1. This is not even Calderon-Zygmunt theory. This is just a simple exercise. Of course, it generalizes to Calderon-Zygmunt operators. And there is this question, problem, whatever you want to call it, that's received a lot of attention, which is what is the Hölder regularity? Or I should simply say the regularity of n and its conjugate in the sense of potential theory, the Lyapunov exponent. In the random case, it is known from a long time ago, this is work of Abel Klein and others, the Barry Simon and Walter Craig and Michael Taylor, etc. So this was much studied. Smoothness of the IDS in the random case, but in the, and that's striking because you see in the free case, the IDS is not smooth, but the randomness smooths you out, all right? In the quasi-periodic case, which is relevant to this conference, it's remarkable that you cannot do better than 1/2 basically, but let me not get ahead of myself. There is an old theorem of Michael Goldstein and myself, 2000, so, which says what? It said that the IDS, so L and N, so of course assume we're in the sense of Avila in the supercritical case, so assume L is greater or equal gamma greater 0. Just make this assumption everywhere on the spectrum. If you only have this for an interval of energies, never mind, then what I'm about to say holds locally on that interval. So for all E in the, so L and N are C alpha, alpha positive for what? Well, not in this generality, of course. So I unfortunately erased the model. For V is a map from the torus into the real line analytic. That's very important for us. More to say about this role of analyticity in a moment. It's very, very subtle issues come up when you drop analyticity. It's analytic, and we had positive Lyapunov exponent. What's the dynamics? Tx is x plus omega mod 1 mod z, and omega satisfied a strong Diophantine condition. So what does that mean? It means that n omega, the distance to the nearest integer, has to be a constant n log n to some power, let's call it b bigger than 1. That's our Diophantine condition for all n greater equal 1. C is just a positive constant depending on omega. So that's the theorem I should have, of course, specified the operator first. So we have a quasi-periodic operator with a general analytic potential. We don't, this is non-perturbative. We don't have large disorder. We have positive Lyapunov exponents, and we get alpha positive. However, in our theorem, we actually had alpha depending on gamma. So we left that on the table. Unfortunately, we left a number of things on the table. Maybe I'll get to that later. So alpha is alpha gamma. Bourgain made the remarkable observation that our proof had some slack in it. I forget when that was, around 04, that alpha is positive independently of gamma. However, the Hölder norm will have to go to infinity as the Lyapunov exponent goes to 0. In other words, as gamma goes to 0. And this is not just empty talk. He showed this delicate, very delicate. So another observation of Bourgain dating to the same time. So he was clearly interested in this issue. Is the following, that another observation of Bourgain is for almost Matthew operator that you have seen many times here, lambda equals 1. This is called critical. This is a very hard case. The spectrum has measure 0 in this case, therefore has to be a Cantor set. So lambda equals 1, almost Matthew critical. He showed that there exists Diophantine omega in Diophantine condition, that is this class. No, it's not this class. So this means that n omega will satisfy a condition of the form Cn to some constant a, and a is bigger than 1. So some Diophantine condition, not necessarily the strong one I had here. He characterizes this by the continued fraction expansion such that the IDS is not in a Hölder class for any alpha positive. I hope I said this in a coherent way. So critical almost Matthew, he was able to exhibit omega characterized by the continued fraction expansion so that the IDS cannot be Hölder continuous. This is satisfying because it shows you that as you send lambda from bigger than 1 to 1, while the Lyapunov exponent remains fixed, the Hölder norm cannot stay bounded. How he did this is a whole story in and of itself. It's kind of amazing. He used Helfer-Sörstad renormalization of semi-classical Schrödinger operators, a double well type analysis, very famous from the 1980s. Again, Helfer-Sörstad. You might be amazed, what does this have to do with a semi-classical double well analysis, tunneling analysis of Helfer-Sörstad, which is microlocal analysis in the style of Jeff. Well, you dualize. No, wait. I thought that his coefficients were bounded below by a big constant, but they had to go to infinity. Silvius, what was his condition exactly? Do you remember? Below by a large constant. And that's all he needed, or did he need some of them to go to infinity? Because for semi-classical analysis, or maybe he took the sum of the, you're correct, so maybe he needed the sum of all the AJs in the Diophantine condition, that had to go to infinity fast enough. Because where's your semi-classical parameter? 1 over h bar will be the sum of the coefficients in the continued fractions. Correct, so thank you. Okay, very good, very good. So thank you. So that was that. Now, many things can be said about this. There were this study of the IDS for quasi-periodic, which might seem, only of interest to specialists, did have a profound effect. For example, for Avila's global theory, and I would be very amiss not to mention this fundamental work. When was that? 02, okay, 01. Where they studied something that Michael and I would have not asked ourselves, but it was really a remarkable foresight of Bogdan-Żytomierska to ask this very question, namely the joint continuity of LE omega as a map, is jointly continuous if omega is not in the rationals. So to say this in a positive way, but you needed positivity, of course, right? So you needed this thing, you had a positivity assumption. Oh yes, of course, so it's always continuous. So this is jointly continuous as long as omega is not rational. It cannot be continuous at the rationals. And this played a fundamental role in Avila's global theory. It was then extended by other authors that in fact you can have continuity in the whole co-cycle, and this is a whole story. The techniques here rely on LDTs that you've heard about, large deviation theorems, and the avalanche principle. So I'm not sure that you heard much about avalanche. So let me kind of sketch out the proof of that theorem of Goldstein and myself. How did we do this? So there is this tool. This stands for avalanche principle, just in case I have to write it down again. And the way we had it back then is you take a bunch of SL2R matrices. In fact, it's enough if determinant AJ is less or equal 1. And then the question you ask is there a tool to kind of build up the norm of a long product of these? And we had 1 less or equal J less or equal N, and we had A1, A2, A1. This is deterministic, has nothing to do with a dynamical system per se. So when can you build up log of norm of a long product in terms of log of norms of smaller pieces? Now this sounds crazy, because what if every pair cancels? What if this is the identity? What if this is the identity? What if this is the identity? Then you would have log norm 1 0. But we want a tool that will hopefully tell us that this is actually growing like n linearly. So in other words, this matrix product growing exponentially. So let me just write down the statement, and then we'll worry about, of course, I'll have to give you the conditions under which this holds. There is an absolute constant, which is constructive, you can specify. So what, we know what n is, it's the number of these matrices. What is mu? And when does this hold? This is a crazy statement if you have pairwise cancellation, because then this would be 0, this would be 0, but here you would have, yeah, with also 0, okay? Not necessarily. If these are big, yeah, if these are big, then you would have a clear contradiction, because that would be of size n, everything else is 0, and here you have n over mu, and of course we want to take mu bigger than n. So provided norm aj greater equal mu greater equal n for all j, okay. So this is not so nice. This says that each factor has to be at least of a norm given by the length of your chain, okay? And then we had a condition that removes this trivial obstacle of having pairwise cancellations. That's norm aj plus 1 aj greater equal root mu, norm aj plus 1, norm aj, all right? And so now you have it. That's the complete statement. There exists an absolute constant C, which is constructive. I don't remember what it is, 10. So that this holds under these conditions. Now, I should say that there is very important follow-up work to this. How we use this, just be patient, please, for a moment. Maybe I keep this, go over here. So Duarte and Klein revisited this whole, so Sirius is here, this avalanche principle, and ended up writing a whole book, very, very nice book, on it and other issues, especially applications thereof, to what? To precisely this paradigm, this question of studying continuity, modulus of continuity of the Lyapunov exponent via this tool and LDT. And so let me just briefly, Duarte Klein removed this unnatural assumption. Why does every matrix have to be big in the length of the chain? So they said norm AJ greater or equal kappa minus 2. So Sirius, if I say nonsense, you have to correct me, yes, please. Root mu, which is at least root n. And then you have these two factors, right? Thank you. Sorry. Thank you. Somebody's paying attention. Thank you. Unforgivable mistake. So what Duarte Klein did is that, and then let me try and get it right this time. Small number, right? Epsilon. This is what Ruben just complained about. AJ plus 1, norm AJ. And what is the condition? That kappa is less or equal some absolute constant that you can actually make, that you can quantify, epsilon squared. Notice no dependence on n. So this should hold for all j, and this holds for all j. And then without writing down this strange combination here again, what they can do is they put here, not this, in red, let me put the Duarte Klein bound is constant kappa divided by epsilon squared. Correct? And they don't need 2x2 matrices. This works for classes, just matrices. So please look at their 2016 book on these topics. Now, coming back to 2x2 cocycles, and we can work with our old avalanche principle. Let's see what happens if we apply it to a quasi-periodic cocycle. You can pick your favorite. You already have seen, from what I understand, in Jake's talk, Sylvia's talk, and so on, course, LDTs. So now we're back here. Analytic potential, omega satisfies a strong Diophantine condition. And in fact, I will state a very special large deviation theorem that was crucial for my work with Michael Goldstein from so many years ago. So I have to just say that my heart is broken because Michael died in December, so it was a devastating loss. So xt log norm mnx. I don't think I have to define mnx for you. It's the product of the first n propagator. So it looks like this, where each of those is given by taking your cocycle and applying the dynamics. So I can't help myself. I write it down. So this is A. It was written on some board here. TJX, but you know what TJX is x plus j omega, and j goes from 0 to n minus 1. And then you want to know what is the failure in the Kingman subadditive ergodic theorem, or the Fürstenberg-Heston theorem, where you then have energy is missing. I tend to make this mistake. Please point out my mistakes. LE, omega is frozen here. When is this greater or equal than a fixed percentage, say, of the Lyapunov exponent? For us now, Lyapunov exponent is positive, so we are here. And then it turns out that if do you have a number of choices, you can state this starting from n equals 1, doesn't make much sense. Or you say for large enough n, be it as it may, you can state it in this fashion. There is another absolute constant which is small. And then you have n. And without going, well, then let me put it like this, that we can put two things here, delta squared or delta. So let me first put the easier one, delta squared n, c positive, little c, big C, absolute constant. Delta squared is the size of the deviation. Absolute constants, okay. So when you put delta squared, they do not depend on the Lyapunov exponent. When you want to put the much sharper delta, which we also proved in that paper, then everything starts to depend on the Lyapunov exponent, because we actually do an inductive argument via the avalanche principle. Where do you get these conditions from? Well, of course, from this LDT, because if you're in the good set, which is the complement of this bad set, and how big is delta? Well, for example, take delta to be gamma over 10, good enough. Okay, then notice that everything starts to click, because you will be able to satisfy this for most x up to a very small set, and this for most x up to a very small set. And so let's see what happens. And the delta versus delta squared is really something for connoisseurs. We don't terribly care, because gamma is a fixed positive number. And so we can take the easier one, delta squared, which wasn't easy for us at all. Turns out Booker also has it in his orange book, and he also has to work hard for that. Silvius, did you talk about this a bit? Sharp, these are called sharp large deviation theorems. Well, so then I don't have to say too much about that. Suppose you're in the good set. So if X, what shall we call it? The good set at scale n for energy E. Fair enough, right? The bad set Bn would be this. So that's, of course, the torus minus the bad set. Now gamma delta is now frozen. You can freeze it. And B and E, where this is exactly defined as that. And then look at, so of course you have to do induction on scale. And I won't take n, I will take L, or why not little n? Let me not mess around here. And little n will be the logarithm of some much bigger scale times a big constant, all right? So in other words, big N will be E to a small constant. Let me be silly and write n divided by the big constant. I just invert this, all right? And now here's the picture. You have avalanche principle. This is 1 up to n. And so now you chop it into pieces. And first, this should be an integer, so take Gauss brackets, integer part. And then this is true up to a small correction. So, and at first, make them all equal, congruent. Now, you can't necessarily pave this with congruent pieces. So here you have one of size L. Oops, the last one is only of size little l. So you adjust little l so that the last one will be between L over 10 and 7 over 8 L, all right? You understand? So you can pave, but here you have to finagle a bit. You can't hope to pave with all the same ones. And then what does avalanche require of you? It requires that you now do pairs. And just for the sake of completeness, let's check something trivial. This should hold for numbers when the AJs are not matrices, but they're numbers. But you see, when your numbers, then everything factors, and you'll see that you get perfect zero on the left-hand side, don't you? So check this. So notice here, I started at 2 because A1 is only canceled by j equals 1. But then you need A2 comes twice. It comes from j equals 1 and j equals 2. So that's why, okay? And then at the very last one, you have AN. AN cancels this AN when you're a scalar, and you don't need it here. Okay, so the left-hand side is identically 0 in the scalar case, or which is equivalent to saying all AJs are diagonal matrices, then everything just factors. So here we have our pairs, right? So this would be A1, A2. And what are the A's? A1 is not the cocycle. It will be a monodromy of the scale Mn. So red is apparently extremely difficult to read. So A1 depends on X, but X is good. And now you will see that we have to even remove more bad points, but you'll see what we have to do. So, but at the first step, I suppose I just remove A1. Then this is the monodromy ML of X at energy E. And now in the good set. So at least this condition will hold with which mu? Just look here. It's the complement of that. So we then know that norm A1X will be greater or equal E to the L minus delta, but L is bigger than L minus delta is greater or equal gamma minus gamma over 10. So I was being ridiculous. I get 9/10 gamma, gamma over 2 would be fine. So here we get L gamma 9 over 10 gamma, right? And what is that? Well, what is L? Oh, L, N, sorry. N, this N. I was debating in my head, should I rename this L? But then instead of doing that, I called this big N. So that is now little n. So let's take stock of where we are. If I make this constant so big that, so take the constant C gamma 9 over 10 greater equal, then for all I care 2. I don't need, isn't 1 good enough? Then what you get here is great E to the log big N, which is big N. No? Okay. So what is big N? Big N is the length of the whole monodromy on the big scale. And it is certainly bigger than the number of factors in this picture because the number of factors is big N over little n. I didn't call it L, I called it little n. So the condition is that each AJ is greater or equal mu, which has to be bigger than big N over little n, but we're making it bigger than big N, and we can make it for free bigger than n to the 100 if we want. But why? If I make it bigger than n to the 100, of course, here I reduce the error by a lot. Yeah, this would be constant divided by big N to the 10, 100,000, whatever you want. Now, what about the dark red pieces? Well, A1, A2 at X, notice I'm only talking about the first two factors, would be M2N of XE. That's this block. And by the same token, the norm, you see, we have to prevent collapse of the product of two of them. This we control from here because I can also bound this from above by this expression. Then I would get, I suppose, 11 over 10 instead of 9 over 10. So I can then say that that's bigger at most n squared. So let's see what this gives us. A2, A1 would then be, I'm sorry if you cannot read this down here, why am I squeezing it? Ridiculous. So M2N XE That is A2, A1. I don't have to write it down again. And we just check that this is greater or equal, but careful, what do we need to do? We need to add more restrictions, right? So we will have to now remove the bad set at scale 2n. We don't terribly care because these are very, very small. All right? These are exponentially small in little n. So we'll, if x is in a good set at scale 2ne, and we'll turn to the sizes of these bad sets in a moment, but just accept that it's good. If it's good, then you have to grant me the same thing as before, but at twice the length. 2n gamma 9/10. And we made that bigger than n, so this is bigger than n squared, no? Because twice, so greater equal n squared. And in this way, you see that you satisfy that. All right, so now you understand what your good x have to be. They have to be good for every single factor, but never mind, because the bad set, you can make the bad set Bn of E less or equal n to the minus 100 if you just make this constant here, this one, big enough, okay? Depending on the Lyapunov exponent. Because we picked delta to be gamma over 10, so gamma is very small, then you have to crank up the constants. This is an absolute one. So maybe it was too many things are called C, forgive me. This C0, then this is a C0 to distinguish it from that C. So you make C0 big enough, then you have that. And then you know what you have to do. You have to take the union of the bad sets at scale E, but you have to apply the dynamics. So J omega, this is the bad set you must remove. To n to take into account what? And little n is ridiculous. That's the number of factors, little m, that you have in this product. But we can be very generous and actually go all the way to big N. Then we've removed more than we need. And we also have to remove, so we have a bad set B twiddle at the big scale N, independence of E. So we have to remove these. And what else do we have to remove? Well, we have to remove it for the dark red pairs. So that's union B2N E shifted. And why not big N? And the total measure will be how big? Well, you have 2n times this, so this will be, being generous, n to the minus 98, no? Actually 99 times a constant, if I'm not mistaken, so we have 98. And what do we gain from all this? So now, how am I doing on time? Okay, very good. So now we understand that the avalanche principle holds up to a tiny set of this measure. Okay, agreed? So with almost overwhelming probability in X, can we do this? Can we factor, quote unquote, the log of the long product into these short products? And now maybe the theorem has to go. What does all this have to do with the theorem? Well, let's see. We will, I just erased it, we will now look at the implications for the Lyapunov exponent, okay? Maybe you can do this in your heads. What is this? This is then, well, I'm writing it down. I can't help myself. I never can. MMXE, okay? And this would be log norm M2N X plus J omega, I suppose. But now be careful, we have to shift like that because the first application of the dynamics doesn't happen at the right edge, right? And then we have plus log norm M little n. If I make a mistake, please tell me immediately. I should call this something else. I'm that pedantic. K goes from 1 to n minus 2, and that becomes a k. And what did we say? We said we can make this as small as we want in this following sense. So we had C, but let's be careful. So this was log of big N. And in fact, there are two C's. I'm being ridiculous. There's this C and this C. So C, C0. This is absolute from avalanche. This is our choice depending on avalanche. And then mu, okay? And no, the number of factors is N. What am I doing? This is the number of factors. I'm being generous. And then I have my mu. And my mu was also N. So then I get basically bounded. This wiggle means up to multiplicative constant is bounded by 1. You might say, well, we can do much better. It doesn't help you. Yes, we can put 1 over n squared. You'll see in a second that doesn't buy you anything, because now, of course, we integrate over the good set. This only holds on the good set, right? As complement of the good set, B and twiddle at E over the good set. Now, but we don't want to just integrate over the good set. We actually want to integrate over everything. Oh dear. So we want to integrate over the whole torus dx. Well, that's cheating. Now break that integral up into the good set and the bad set. On the good set, this is fine. On the bad set, we will do this. So less or equal 1 plus, that was this one. The good set has measure at most once, so nothing happens. But then we have the bad set times the worst possible bound you can think of. And the worst possible bound is something terrible where you just bound this monodromy by e to the cn. So it's exponential in big N. That means that you will pick up n up to a constant that you put in this twiddle. Understood? Bad set times the worst possible estimate you could put here. But notice, the bad set is n to the minus 98. So this whole thing is bounded by 1. Oh, but now we can integrate over the full circle. And of course, what happens when I integrate this? Don't I get ln e? That is the Lyapunov exponent of this guy times big N, because 1 over n this is the Lyapunov exponent ln. Now what's going on here is interesting. We have minus, what is this creature? That's L2 little n times 2n, right? That's the integral of this, times n minus 1. What am I doing here? N minus, this is m minus 2. This is the number of factors. The number of factors. And the number of factors is, what is the number of factors for me? It's big N divided by little n plus a correction, big O1. Agreed? Because I'm counting how many cuts I make. And the number of cuts I make is big N over little n, but I could be off by 1 or 2 or something like that. So I just write it lazily like that. So forgive me for my typos. Then I have to multiply by little m minus 1. That's the number of terms, but you know, this is off by big O1 anyway. So let's write big N over little n. And what error did I just make? If I shift this by order 1, then I pick up little n times a number. So therefore, my little n, my 1 here, is optimistic anyway, because through this fudging, I will lose a little n. And little n is log big N. Agreed? That's why I said it doesn't help you to improve this, because you can't beat this error. All right, so if you're with me, this is what we have here. Let's quickly wrap this up. This is n, ln, and then I have big N over little n. And this difference is bounded by that. What's the upshot? We don't need avalanche anymore. The upshot is we want to clean this here. So big N over to the other side. E I will suppress from the notation. Then I have minus 2L2N plus, and this cancels, ln, and this is bounded by log n over n. That's the bound. And now we're going to do something sneaky. We're going to repeat this whole procedure with 2n. Replace n by 2n. But use the same little n. All right? So you get this identity twice. But here you now have L2n. And now subtract them from each other. And you get from this game the rate of convergence of Lyapunov exponents. Something has to go. This picture goes and this stuff goes. So then what we have found is L2n minus Ln. In fact, L2n is smaller than Ln. No, that's less or equal than this is greater equals 0. And that's bounded by constant log n over n. I'm tired of all these c's, so let's write that. That's a little lemma, no? When does this hold? We proved it subject to that, and actually what I just did doesn't really need this for the experts, the sharp large deviation estimate. You could have had root little n there, doesn't make a difference. Where are we using the sharp one? That you really have little n, you'll see it in a second, if I still have a second. So now pass to the limit here, you can do a dyadic decomposition, and you see, of course, that ln minus L, that's the object you want. Uniformly in E, because all we needed was the lower bound on the Lyapunov exponent. This is now, right? Add up, telescope this. So this is, you will find this old thing in my paper with Michael Goldstein. And so now what do we do with this? Don't we want to control the modulus of continuity? Okay, so it is extremely expensive to differentiate the Lyapunov exponent E. In fact, you can't do that. This is an infinite volume object. So let's go to finite volume. At what expense? Log n over n. We have no idea what n is yet. So we pay log n over n plus ln E minus ln E prime. Now, let's do better. We want to differentiate this in E. Horrible idea, because then I would pay E to the constant n, no? If I blindly differentiate the exponent in volume n in E, I will pay an exponential price for it. Because ln is log norm mn, think about it. It's this, it's the average of that. If I differentiate this creature, I will bring out, I will have to divide by norm of this. All right, so you run the danger of paying an exponential price. And in fact, you do. Now, let's be sneaky and try and reduce the scale. So we use this. At the same expense, we can now sneakily replace this by log n over n plus LLE, no, you see L and L little NE minus L little NE prime plus L2NE minus L2NE prime. And now we're in business, because now we will differentiate in this, we pay exponentially in little n, but that's polynomial in big N. Okay, so now let's get rid of this. Let's get rid of that. So we have log big N over n plus an exponential cost here. Let's just write E to some constant. What have we not used? Big B little n. Absolute E minus E prime. Now this equals n to C0b, no? Look how we picked little n. Not here anymore. Little n was this silly C0 log big N, well, integer part thereof. And so, and now optimize this inequality. In fact, who cares about this log? bound this by root and then set that equal. And you see that what you have to do is you have to pick n to be what? Let's be very slow. C0b by my choice, a half. I got afraid of the log, no? A half. And that has to equals for these to balance e minus e prime to the -1. Did I do this right? Yeah, but doesn't this mean that now my scale n, finally, we know what the scale n has to be. E minus e prime to the minus beta, where beta is 1 over this big constant. And then, if you do this, you see that this whole shebang is bounded by e minus e prime for cosmetics reasons. Like, let's write 2, how nice. And then we get beta, and that's your Hölder bound, e minus e prime. You see? So you get Hölder bound, but notice carefully that our C0 depended on the Lyapunov exponent. So that is why our beta in the original, this is the original argument of Misha Goldstein and myself. That is why our Hölder exponent depended on gamma, which was the lower bound of the Lyapunov exponent. Bourgain then took a very hard look at this and saw a way to avoid that dependence. And I think I should stop here. Thank you very much. I omitted many things that came after and so on. So Silvius is a master of this type of argument. Look at their book, Duarte Klein, 2016. Yes, please. Yeah, so this is a decreasing sequence because how does it go? Where is an eraser? Here. This is the subadditivity, no? Right, so first of all, what is ln? Ln is integral log norm mn of x dx. You can do this. And then you do 2n, and norm 2n is less or equals, all right? So you then get L2n, what is it? 2 ln, but this is normalized, all right? So then you get 2n L2n less or equal 2n ln, and that means L2n less or equal ln, just by subadditivity of log norm mn. Okay.